Okay. In this lecture, I am going to continue the Maxwell-Boltzmann distribution. In the last lecture, I had stopped the derivation of Maxwell-Boltzmann distribution at this stage, that is summation I 1 plus ln ni equal to 0. I had stopped the derivation at this stage in the last lecture. Now let me continue from this. See, what I am going to do, I am going to multiply both sides by dni. So if I multiply, it will get summation over I 1 plus ln ni into dni equal to 0. If I multiply both sides by dni, I will get dni here. Right hand side 0 into dni is 0. Now, let me separate this into two parts. Sum over I dni plus sum over I ln ni into dni. I will separate this into two parts equal to 0. What is summation dni? Listen, from the change in population in the ith level, okay, and change in the population in the next level, jth level, for example, right? So if you sum up the change in all the levels, the total change should be equal to 0 because total number of particles is constant. Okay, therefore this should be equal to 0, right? Then so we can write summation I ln ni into dni equal to 0. Okay, let me write the next step. So sum over I ln ni into dni equal to 0. I will take this as equation number 1. See, we have actually maximized the function w, okay, for which what we did, we took logarithm and then we differentiated this with respect to dni and we substituted this value equal to 0. Yeah, this is the usual way of finding the maxima or minima, okay, but in this case we will get maxima, right? But there is additional problem, okay, exists here. What is that? Total number of particles and total energy are constant. These two are constants. So keeping these two constant, you have to maximize. For this, we need some special technique. Yeah, we have a method in mathematics called Lagrange's Undetermined multiplier method. Okay, so whenever you want to maximize any function, keeping some quantities constant, okay, we usually adopt this method called Lagrange's Undetermined multiplier method. Okay, Lagrange's Undetermined multiplier method. This is the method we follow. Okay, according to this method, see what I am going to do. Summation number of particles in each level should be equal to total number of particles. If I differentiate both sides, what will get? Summation of dni. Since n is constant, differentiation of n will give you 0. Right? I will take this as equation number 2. Similarly, summation ni into ei, number of particles in the ith level, summation Ni into dEi, number of particles in the ith level, into energy of the ith level. Okay, see, you know real energy is for each level is obtained from quantum mechanics, and it is independent of temperature, right? Usually, right? It is independent of number of particles actually, right? So if I differentiate this, right? Okay, number of particles in the ith level into energy of the ith level will give me total energy of ith level. Similarly, for all other levels, you calculate number of particles in that level and the energy of that level, then add everything. If you sum up everything, you will get the total energy. Okay, so if I differentiate both sides, okay, you have to keep EA as such, because EA does not change when you move from one distribution to another distribution, because our goal is to find the most probable distribution. Okay, when you move from one distribution to another distribution, number of particles in one level, okay, may increase or decrease, but energy, this energy, it is the quantum energy of the quantum state. These energies never changes. Okay, so EI, keep EI as such. If I differentiate Ni, I will get dNi equal to total energy is constant. So if I differentiate, I will get 0. So I will take this as equation number 3. Now what I am going to do, I am going to multiply equation 2 by an undetermined multiplier, Lagrange undetermined multiplier alpha. Okay, and I am going to multiply equation 3 by another multiplier, Lagrange undetermined multiplier beta. Okay, and then I am going to add equation 1, 2 and 3. Right, see what I am going to do, I will write in the next page. So I am going to add equation 1 in such a manner that I am going to actually add equation 1, 2, 3. Okay, before that I have to multiply equation 2 by alpha and equation 3 by beta. Okay, so I will multiply equation 2 by alpha and equation 3 by beta, then I will add all these things. Okay, so if you see equation 1, in equation 1 we had this quantity in the left hand side, summation ln Ni into dNi, and in equation 2 we had summation dNi. If I multiply by alpha, I will get alpha into summation over I into dNi plus beta into summation Ei into dNi. This is equation number 3, and that's summation. In all these equations, right hand sides are 0, so if I sum up, I will get 0 only. Okay, so in all these 3 terms I have summation, so I will take summation as common. So I will get ln Ni here plus alpha here plus here I will get beta into Ei, and I will take dNi common and keep it in the right hand side equal to 0. I will keep it here. Okay, dNi is common, so I took dNi as common term and I kept here. Okay, now see, this quantity should be equal to 0. What does it indicate? It indicates that, okay, for this to be valid, for this equation to be valid, okay, either this should be 0 for all the level, or this should be 0 for all the level. But you know very well, when you move from one distribution to another distribution, okay, population, right, in say if you take some ith level, the population in the ith level may increase or may decrease. Okay, rarely it also may be 0, but it is not 0 always. That's the point. Okay, when you compare one distribution and another distribution, okay, population in the ith level usually increase or decrease. Very rarely, okay, it remains same. Okay, so dNi can be 0, but it is not always 0. That's the point I like to say. So dNi in general is not equal to 0. Therefore, for this equation to be valid, this quantity which present in the square bracket, that should be 0 for all the level. Okay, so what's the quantity we have? On Ni plus alpha plus beta into Ei equal to 0. This should be 0 in order to satisfy this equation. Okay, now I'll bring this alpha, beta, Ei to the right hand side, so I can write this as ln Ni equal to minus alpha minus beta into Ei. Okay, and we also know that ln is nothing but log base E. Ln is nothing but log base E. So this is minus alpha minus beta into Ei. So what is Ni? If I remove log, this E will go here and this term will come in the power of E. So E power minus alpha minus beta Ei. You can also write this as Ni equal to e power minus alpha into e power minus beta Ei. Okay, we'll get an equation like this. This equation will give you the population in the ith level of the most probable distribution directly. What actually we want? We want population in the ith level. Okay, population in all the levels actually. So this is a general expression. Population in the ith level of the most probable distribution is what we actually want. Okay, if you know that information, you can calculate the equilibrium properties, right? Yeah, but right now alpha and beta are undetermined multipliers. We don't know what's the value of that. So how to find the value of e power minus alpha? Okay, and this is beta, right? Yeah, see, let me do that in the next step. So I'll take this as equation number 4. It's a running equation. Okay, then. So let me write the next page. So this can be, you can find the e power minus alpha value as, let me write here. See, we know very well summation Ni, that is population. Okay, population in each and every level, if you add, you will get the total population or total particles, total number of particles. Okay, number of particles in each level, if you add, you will get total number of particles, right? Summation L put I. Okay, sum over I. What is Ni from equation 4? Ni is nothing but e power minus alpha into e power minus beta epsilon Ei is equal to n. E power minus alpha is constant, so I can keep it out. E power minus alpha into summation sum over I e power minus beta into Ei equal to n. Or we can also write this as e power minus alpha equal to n by, okay, n by summation over I e power minus beta into Ei. This is the value of e power minus alpha. Okay, now I'll substitute this quantity in equation number 4. So I'll get, and what about this beta? Listen, beta is also a Lagrange undetermined multiplier. I am going to derive and show that beta should be equal to 1 by kBt. Okay, now listen, I am going to derive this in at least 2 or 3 lectures after. Okay, after 2 or 3 lectures, we are going to see how to derive this. But right now, I'll give the value. Okay, so beta value is 1 by kBt. Anyway, we are going to show that beta is equal to 1 by t after 2 or 3 lectures. Okay, so let me substitute this value and this value in equation 4. Therefore, you will get, so equation 4, you will get equation 4 as 4 will become Ni equal to, in the place of e power minus alpha, I will put this capital N divided by sum over all the I values. Okay, e power minus beta value is 1 by kBt, so I can write this as Ei by kBt into here we have e power minus beta I, so e power minus, in the place of beta I will put 1 by kBt, so ei by kb into t. We can also, I will bring this n this side, so we can also write this as ni by n equal to e power minus ei by kBt over summation e power minus ei by kBt. Okay, this is the expression for Maxwell-Boltzmann distribution, okay, for non-degenerate energy levels. If energy levels are non-degenerate, yes, you can use this expression as Maxwell-Boltzmann distribution. Okay, what is the use of this expression? Right, what's the importance? The importance is that you will get population in the ith level of the most probable distribution directly. Okay, this expression, okay, is applicable for most probable distribution. You can find the number of population in each level in the most probable distribution directly if you know the value of n and the value of ei and temperature. N value will be given, temperature you know, ei should be obtained through quantum mechanics. Okay, this energy may be translation levels, maybe rotation levels, or maybe vibration levels, right? So using quantum mechanics we have to find this. Then if the total number of particles and temperature are given, yes, you can calculate population in each and every level in the most probable distribution. Okay, remember this formula is applicable for energy levels which are non-degenerate. Okay, and this denominator quantity, this quantity, right, is called as molecular partition function. It's called as molecular partition function, okay, which I am going to represent by the symbol capital Q. Molecular partition function, I am going to represent this side by the symbol capital Q. Remember, this capital Q depends on, let me write in the next page. The capital Q is actually a function, right? Q is a function of number of particles, volume and temperature of the system. If number of particles changes, yes, partition function changes. Volume changes, yes, partition function changes. If temperature changes, yes, partition function will change. Okay, so Q is called molecular partition function. Why it is called molecular partition function? The reason is the energy levels, okay, in which we are distributing the particle, okay, those energy levels are actually molecular energy levels. Molecular rotation levels, molecular vibration levels, molecular translation levels, right? Since they are molecular energy levels, okay, we call this partition function as molecular partition function. Okay, then. Now, so what is Q? Q is equal to summation I e power minus ei by kBt. This is the expression for Q for non-degenerate case. Non-degenerate energy levels. If energy levels are non-degenerate, yes, you can use this formula. And here, this sum over I, okay, indicates that sum over, right, this I this sum over I, okay, it is actually called sum over energy states. Sum over energy states. Okay, for non-degenerate energy levels, okay, this summation symbol should be taken for sum over energy states. You know very well, if all the energy levels, if each energy level contains only one state, you can call it as energy level or energy state. Nothing wrong in it. So this is actually called sum over energy states. Okay, yeah. So now I have given the Maxwell-Boltzmann distribution, the expression for Maxwell-Boltzmann distribution for non-degenerate system. Suppose if the energy levels are degenerate, okay, for degenerate energy levels, right? If energy levels are degenerate, then we have to follow the same method, but the initial formulas are different. Okay, what is meant by that? See, suppose assume that I have a system in which energy levels, okay, say ground energy level has say number of states. Say for example, I have G0 states, okay, associated with the ground energy level, and energy of the ground energy level is represented as E0, and you know very well, usually the ground energy level, energy of the ground energy level is taken as 0. Even if it is not 0, we have to convert it into 0. Okay, that's the point you should keep in mind. Then the next level, the first excited level, whose energy is E1. Listen, only the ground energy level is 0. First excited, second excited, other levels, okay, the energies of other levels are not 0. Okay, and the first exit level, let us say the first exit level has some degenerate states. Let the number of degenerate state equal to G1. Okay, G1 represents degree of degeneracy of the first excited level, right? Or number of states in the first excited level. Similarly, number of states in the second excited level, okay, can be given as G2. And like that, in each level we have certain number of states. Okay, and number of particles, let us assume number of particles in the ground level be N0, and number of particles in the first exit level be N1, N2, etc. Similarly, we have some ith level, right, which has some number of degeneracy Gi, and number of particles in the ith level, let it be Ni. Like this, we have many states. Okay, for this case, if the particles are distinguishable and independent, okay, thermodynamic probability can be obtained using the formula n factorial into pi into Gi power Ni by Ni factorial. We have to use this formula to find the thermodynamic probability of the system. Okay, whenever the energy levels are degenerate, we should use this formula for distinguishable particles. Right. Now what we have to do? You know the technique. Take logarithm, then differentiate this ln W with respect to dni, put the value equal to 0. Okay. Then apply Lagrange undetermined multiplier technique. Okay. Finally, you will get the expression for Maxwell-Boltzmann distribution. I am going to give you the final expression. I will leave this to you as an exercise. Okay. You try to find whether you get the expression or not. Okay. So, what is the final expression? The final expression is this: Ni by N equal to Gi into e power minus Ei by kBt over summation Gi into e power minus Ei by kBt. Yeah. So this is the formula for, this is the expression for Maxwell-Boltzmann distribution in the case of energy levels which are degenerate. Right? If a system containing energy levels which are degenerate, then we can use this formula. Okay, for as this is the expression for Maxwell-Boltzmann distribution. Okay. And as said before, this denominator quantity is called molecular partition function, which is denoted by the symbol Q, and Q depends on number of particle, volume and temperature. Q is called molecular partition function for n particles. Molecular partition function for n particles. Okay. Yeah. Now, before going to discuss some of the features of this Maxwell-Boltzmann distribution, let me talk something about this partition function, then we'll come back to the Maxwell-Boltzmann distribution. Okay. So now I am going to discuss about partition function. Right here. So I am going to discuss about partition function. Here I am going to talk about capital Q. Capital Q means molecular partition function. Molecular partition function, okay, for n particles. Molecular partition function for n particles. Okay, why I am stressing this term n particle, because we are also having a single particle partition function, for which I am going to use a small q symbol. We will discuss that later. So the difference between molecular partition function and single particle partition function is that molecular partition function depends on number of particles, whereas single particle partition function, it does not depend on number of particles, it depends only on volume and temperature. Yeah, we are going to discuss everything as we go along. Okay. Now, for distinguishable particles, we have two expressions. One is Gi into e power minus ei by kBt, and this expression is applicable for energy levels which are degenerate. And we have one more expression, Q is equal to summation e power minus ei by kBt. This expression is applicable for non-degenerate energy levels. Okay, this is for non-degenerate case. Okay, and this is for degenerate case. Okay. Now, here sum over I indicates sum over energy states, whereas here the summation I indicates sum over energy levels. Okay, so here this summation I indicates sum over energy levels, whereas here this summation I indicates sum over energy states. Okay. Now, before going further, let me give some information here. If you expand this summation, you will get Q is equal to, first if I equal to 0, I equal to 0 means ground state. Say if I equal to 0, I will get degeneracy as G0 into e power E0, I should put E0 by kBt, but you know very well E0 is 0. Usually in statistical thermodynamics, we take the energy of the ground level as 0. So if this is 0, then the total power becomes 0. So e power 0 is 1. E power 0 1 means 0 into G0 into 1 will give you G0 plus. This is for ground state or ground energy level. For the first energy level, I should put I as 1. So you will get G1 into e power minus E1 by kBt. Remember, E1 is not 0. Only E0 is 0. Okay. Similarly, we have G2 into e power minus E2 by kBt. Okay. Plus etc. etc. You can expand this as like this. Similarly, you can expand this function, okay, as Q is equal to 1 plus e power minus E1 by kBt plus e power minus E2 by kBt plus etc. etc. Right? Keep this point in mind, which is very, very important. Now, to understand what is this Q, right? I'll take ground state, okay, for ground energy level. For ground energy level, you can use this formula or that formula, you'll get the same expression, so that's not important here. For ground energy level, you know very well, number of particles in the ground energy level is represented as N0. Okay, Ni means number of particles in ith level. Since now we have taken ground energy level, Ni should be represented as N0. And degeneracy, Gi, should be represented as G0. But G0 is equal to 1 for most systems. For most cases, right? For most rotation level, vibration level, right? For most cases, degeneracy of the ground state is 1. Not always. For most cases, degeneracy is 1. Okay, ground state degeneracy is 1, right? Then energy of the ground state, right, is usually Ei. Okay, Ei for ground state it is represented as E0, and you know very well in statistical thermodynamics we fix E0 as 0. If I substitute these values in this expression, you can use this or that. Okay, both will give same. What will I get? Q is equal to, I will substitute in this expression. Okay. Or you can use this expression also, right? Degeneracy of the ground state is okay. One second. Yeah. Let me use the Maxwell Boltzmann distribution. I'm sorry. So what is the Maxwell Boltzmann distribution? Ni by capital N equal to Gi into e power minus Ei by kBt by Q, where Q is a molecular partition function for n particles. Okay, you can use this formula. This is for degenerate levels. You can also use non-degenerate level. Okay, both will give same answer. So what I am going to do for ground state, instead of Ni I should put N0. Okay, put here N0 divided by total number of particles N equal to degeneracy. Instead of Gi I should put G0, but we know very well G0 is 1 for most cases, so that is 1. And instead of Ei I should put E0, but E0 is 0, so this becomes 0. E power 0 is 1 divided by capital Q. So what is Q from this? From this, capital Q is equal to, right, if you rearrange you will get capital N by N0. What does this indicate? It indicates that molecular partition function for n particle is equal to total number of particles divided by number of particles in the ground state. Okay, this is the formula. Now keep this in mind. Okay, suppose if I give Q value as 2, what does this indicate? Okay, suppose I give, next page. What does this Q value equal to 2 indicates? Okay, for this purpose you can take total number of particles as 100. If total number of particles is 100, you know very well Q is equal to capital N by N0. To get Q equal to 2, see total number of particles is 100. Okay, if I put N0 as 50, then I will get Q equal to 2, correct? So Q equal to 2 indicates that out of 100 particles, 50 particles out of, right, total, right, out of 100 particle, 50 particle must be present in the ground state. Okay, so Q equal to 2 implies that 50% of population, 50% of population exists in the ground state. That's the meaning. Okay, suppose if I give Q equal to 4, what does this indicate? To find Q value, you take n value as 100 because you will get percentage directly. Okay, if I take n equal to 100, so q is equal to n by n0 is the formula. N is 100. To get q equal to 4, what value should I put for n0? 25. Okay, so 100 by 25 is 4, which means 25% of population exists in the ground state. So q equal to 4 implies that 25% of population exists in the ground state. What about the remaining 75%? Remaining 75% of population are distributed in the excited levels. Okay, so that's the point you should keep in mind. That's the meaning for a partition function. Okay, good. Then next point, see partition function q. What is q? Q is equal to n by n naught. That's the formula, you know. N by n0. N is number of particle, n0 also number of particle. So you will never get any unit here. Okay, so what's the point? The point is this: q is a dimensionless quantity. Q is a dimensionless Q is a dimensionless quantity. There is no unit for Q. This is the second important point you should keep in mind. Okay? Yeah. Then the next one. So now you know what is the meaning for partition function, right? Now I'll give some more information on partition function. What's that? Suppose what happens to the partition function when temperature approaches 0 Kelvin. Temperature approaches 0 Kelvin means you should cool the system, or you should remove the heat. Okay, you should remove the heat from the system. If you remove more and more heat from the system, what will happen? The particles which are present in the higher energy level, they starts to come down. They starts to occupy lower levels. When temperature approaches 0 Kelvin, okay, what will happen to the partition function? Okay, and what information we get from the partition function? Yeah, we'll see that. We'll see that. Listen. First, I'll take a non-degenerate case. For non-degenerate case, okay, you know very well. Q is equal to, for non-degenerate case, Q is equal to, you can write Q as 1 plus e power minus E1 by kBT. In the last page I wrote this. Okay, in the, this expansion I gave already. Okay, this is how you can expand the partition function for non-degenerate case. Okay, if temperature approaches 0, suppose if I put 0 here, in the place of temperature you put 0. Something by 0 is infinity. Okay, you will get infinity here. E power minus infinity is 0. Okay, you know something by 0 is infinity. And e power minus infinity is also 0. That is 0. Therefore, this term becomes 0. Similarly, this term becomes 0. So, all these terms, okay, becomes equal to 0 when temperature approaches 0 Kelvin. So, when temperature approaches 0 Kelvin, right, all these quantities become 0. Therefore, Q becomes equal to 1. Okay, partition function, right, molecular partition function for n particles becomes equal to 1 when temperature approaches 0 Kelvin. You know very well, when you will get Q equal to 1, you know the formula. Q is equal to total number of particles divided by number of particles in the ground state. Okay, if total number of particles is 100 and if number of particles in the ground state also 100, then only you will get the answer as 1. So Q equal to 1 means isn't the entire population. Okay, suppose if we have 100 particles, if all the 100 particles are present in the ground state, okay, then only you will get Q equal to 1. So Q equal to 1 indicates that all the particles, okay, occupy the ground energy level of the system. Right? This is possible when temperature approaches 0 Kelvin. Right? This is for non-degenerate case. What about for degenerate case? For for degenerate case. Okay, for degenerate case we can write Q is equal to G0 degeneracy of the ground state plus G1 into e power minus E1 by kBt plus G2 into e power minus E2 by kBt plus etc. etc. Okay, this is how we expand. Now, when temperature approaches 0 Kelvin, okay, when T approaches 0 Kelvin, if I put T 0 here, this term becomes 0, 0 into G1 becomes 0, this term becomes 0, 0 into G2 also becomes 0, so the entire term becomes 0 when temperature approaches 0 Kelvin. So the only term that remains here is G0. So Q is equal to G0, right, when temperature approaches 0 Kelvin if the energy levels are degenerate. Okay, if a system in which if energy levels are degenerate, then when temperature approaches 0 Kelvin, okay, partition function will be equal to the degeneracy of the ground state, because all the molecules, right, all the particles will come to the ground energy level, right. So in the ground energy level we have G0 states, so all the 0 states are occupied by particles, therefore Q is equal to G0, right. Yeah, then and we know very well that for most cases the degeneracy of the ground state is 1. So Q is equal to 1 for most cases, but there are a few systems where Q need not be 1, because in those cases the ground level may have some degeneracy. Okay, then the next point, what happens when temperature approaches infinity? Okay, let me write in the next page. What will happen when temperature of the system approaches infinity? That is, if you supply more and more heat to the system, what will happen? Yeah, by physical sense you can say that as you supply more and more heat, the particles gains heat energy and goes to the higher energy levels. Okay, so population in the higher energy level starts to increase and population in the lower energy level starts to decrease. Okay, when temperature approaches infinity, what will happen? That's the point. Okay, see, for non-degenerate case, for non-degenerate case, let me write here. Q is equal to, you know the formula, Q is equal to 1 plus e power minus E1 by kBt plus e power minus E2 by kBt, right, plus etc. etc. If temperature approaches infinity, okay, if I put infinity here, something by infinity is 0, you know very well, something by infinity is 0. So this power becomes 0. E power 0 is 1. So Q is equal to, the first term is 1, second term also become 1, third term also become 1, plus 1 plus 1 plus 1, etc. etc. Listen, how many states that are actually available, right? All the available states are, up to the available states you will get 1. So Q is equal to number of available states. Number of available states. Simple. If a system consists of say 100 states, all the 100 states, okay, I will contribute 1, so you will get 100. If the system consists of 1000 states, all the 1000 states will give 1. Okay, each state will give 1. Therefore, we have 1000 states, so you will get the Q value equal to 1000. Okay, so that's the point. Now, suppose I have degenerate levels for degenerate case. If energy levels are degenerate, then what to do? Yes, you know the formula, Q is equal to G0 degeneracy of the ground state plus G1 into e power minus E1 by kBt plus G2 into e power minus E2 by kBt and so on. Okay. Now, when temperature approaches infinity, okay, if I put infinity here, something by infinity is 0, so I'll get e power 0, e power 0 become 1. So this become 1. Similarly, this become 1. 1 into G1 is G1. So Q is equal to G0 plus G1 into 1 is G1 plus G2 into 1 is G2 plus G3 plus etc. etc. Okay. So you should add degeneracy of each energy level, okay, up to the available energy levels. Okay. So Q is equal to sum over Gi. Sum over Gi. Sum over energy levels we should take, right? So you should sum up degeneracy of each level up to the available energy level we should consider. Okay. So this is the partition function. Okay, this is the value the partition function will attain when temperature approaches infinity in the case of energy levels which are non-degenerate. I'm sorry, which are degenerate. Right? Yeah. Keep all these things in mind. I stop here. We'll continue this lecture in the next class. Okay? Yeah. Thank you for listening.